Hello everyone. We're going to be completing online lecture 9 today, and this is the penultimate lecture. So, which means we're going to have one more lecture, which is lecture 10 on Thursday. My plan for today is to complete the equations of motion for the rolling coin, and if we have time, we will look at a very simple problem where we make use of the Lagrange multipliers. Then in the next lecture, which is lecture 10 for MA 5030, we will be looking at the equations of motion of a spinning top. Okay. In the meantime, I hope all of you are staying safe and staying healthy. We're almost there. It's the end of the journey for MA 5030. All right. So plan for today is the following. Okay. So aim for today. We will complete the equations of motion for a rolling coin. Okay, and then I will be posting the elaborate lecture notes for these, as well as for parts of variational calculus of variations, where it's a part that we have not actually had the time to cover in class. So I'll be posting those lectures on Carmen. Okay, so we'll be posting lectures on Carmen. Posting elaborate lectures on Carmen. All right. So what we have done so far is the following. We started off with the situation of the rolling coin, right? I just want to recap things that we have done in the past. Okay, so we started off by looking at the configuration coordinates of the rolling coin. Okay, looked at the configuration coordinates. Of the rolling coin. Okay, and these configuration coordinates are the following. We had 6 of them, right? We had x, y, and z. These are the location of the center of mass, of the coin, and we had 3 angular quantities, phi, theta, and psi. I just want to write that psi properly. So this is psi, the Greek letter psi. These represent the Euler angles. Okay, these are the Euler angles. Okay, this represents the angular position of the coin at any instant in time. Okay, so the angular position, angular information about the motion of the coin. Right, so these are the 3 things that we looked at. Then we also looked at the 3-1-3 sequence of Euler angles. Okay, so we looked at the 3-1-3 sequence of rotations. Okay, this is the other thing that we looked at in the previous class, and of course I said that one can have different types of rotational sequences as long as one makes sure that the geometric singularities are taken care of. And we also noticed that there were 2 types of singularities. There was a physical singularity, this is during the reference configuration of the coin. Okay, during the reference configuration of the coin. Okay, so this was during the reference configuration of the coin. Right, and we also had the geometric singularity. The geometric singularity is especially considering the position of angle theta. If the angle theta is either 0 degrees or 180 degrees, then we see that this is going to result in the phi and the psi rotations giving you the same information, so we will not be able to distinguish between the two. Okay, so we also had a geometric singularity. Let me change the color for that back to usual. Okay, so we had the geometric singularity. Okay, and this was for the situation of the angle theta being either 0 degrees or 180 degrees, which means that to avoid the geometric singularity we need to have theta to be between 0 and 180 degrees. Okay, so theta has to be between 0 degrees and 180 degrees to avoid this. Alright, so these are the things that we saw, and we also looked at the rotation matrices for the 313 sequence. I'm just going to very briefly and quickly write them out and also show you the 313 sequence here. Okay, so this is the 313 sequence with the rotation matrices as shown. Okay, sequence of rotation. Okay, here is the sequence. If I can bring in my figure from the previous time, I had it copied, so I'm just going to paste that here. I hope you can all see this clearly. Okay, I'm just going to maybe expand it a little more. Okay, so here is the 313 sequence of rotations. Okay, and maybe I can crop it up a little more so that we don't waste as much of our space here. Okay, alright, so here is the 313 sequence, and in the 313 sequence we see that the first rotation is performed about the 3-axis. Okay, in this case this is the 3-axis. Okay, and then the second rotation we see is performed about the 1-axis. Okay, so this is the axis about which the rotation is performed. This is the 1-axis, and then the third rotation is performed about the 3-axis again. Okay, this is about the 3-axis, and so this is why it is called as a 3, 1, and 3 rotation. Okay, and based upon this we were able to write the rotation matrices in the following form. Okay, so this was again from the previous lecture. I'm just rewriting some of this information from before. Okay, so the rotation matrices, rotation or coordinate transformation matrices from one system to another. This was from lecture 8. Okay, and these were the following equations. We had in the 3-axis first rotation we had going from ex, ey, ez to e1 prime, e2 prime, e3 prime. Okay, so this is in the first rotation. And this was let me change the color of this line here. Okay, so in the first rotation we had going from e1 prime, e2 prime, e3 prime was what we ended up with. Okay, and as usual this is going to be the following, and for me I need to write this because I'm going to be making use of these rotational matrices. So this is going to be cos phi sin phi 0 minus sin phi cos phi 0 0 0 1. Okay, and then this will be multiplied by ex, ey, and then ez. Okay, and then likewise I had the second rotation, and we call this as the first rotation matrix R1. Okay, so this was typically called as R1, the big matrix that you see here, one's filled with cosine phi, sine phi, and so on. The second rotation okay, is going to be the following. We go from the single prime to the double prime coordinate frame. Okay, so this is going to be E1 double prime, E2 double prime, E3 double prime. The rotation is about the E1 prime axis, which means that the E1 prime and the E1 double prime axis coincide with each other. So this is going to be 1, 0, 0, and then 0 cos theta, sine theta, 0 minus sine theta, and then cos theta. This is the rotation matrix for the second one. Okay, and this is going to be E1 prime, E2 prime, E3 prime, and then my third rotation is going to be the following. It's going to be back to E1, E2, and E3. I'm just going to change the color here. So this is going to give me E1, E2, E3. Okay, and I'm going to have this matrix here as cosine psi, sine psi 0, minus sine psi, cosine psi 0, 0, 0, and then 1. And then this is going to be my double prime coordinate frame. E1 double prime, E2 double prime, E3 double prime. Okay, these were the three rotation matrices. This was the first three-axis rotation about the EZ direction. Okay, so if I call this as, let's say that this is frame F, 1 or F0, which is the same. Okay, so this is I think I called this as frame F1 in the previous situation. This was frame F2, this was frame F2, this was frame F3. Okay, this was frame F2, and this was frame F4, and this was frame F3 as you see here. And then what you can see here is that omega of F2 slash F1 is going to be phi dot in the EZ, and then we have omega of F3 slash F2 is going to be theta dot E1 double prime or E1 prime, it does not make a difference. And then lastly I have omega of F4 slash F3 is going to be psi dot in the E3 double prime or E3 prime, it does not make a difference here. Okay, and frame F1 does not rotate with respect to the inertial frame. Okay, so I just want to make a note of that. Frame F1 omega of F1 slash F0 is equal to 0, where F0 is an inertial frame. Alright, and so using these we had decided that okay, the angular velocity of the rigid body can be written in the following form. So this implies that omega of the coin, okay, and you can write this as omega of F4 slash F3 plus omega of F3 slash F2 plus omega of F2 slash F1. Okay, or you can essentially say that this is going to be omega of F4 slash F0. Okay, and so omega of the coin, we wrote this in the previous class. Omega of the coin is going to be phi dot in the EZ, then I'm going to have theta dot in the E1 double prime, and then psi dot in the E3 prime, but E3 prime is the same as E3 double prime, so this is the same as phi dot EZ, and then theta dot E1 double prime, and then psi dot E3 double prime. Okay, this was the expression that we had in the previous class. And one thing that we wanted to note was that this frame F3 was actually fixed to the coin but was not rolling with the coin. Okay, so that's something that you want to keep a note of. The frame F3 was fixed to the coin but not rolling with the coin. Okay, and what I want to make a note of it is that this is mostly for the sake of convenience, and I would want you to refer back to lecture 8 for that. Okay, this is mostly for convenience. And refer to lecture 8. Okay. All right, so we have omega of the coin. Now what I want to do is I want to write omega. Of course, this omega is written with respect to the Euler basis, so that was also something that we had looked at in the previous class, right? So we had the Euler basis. Okay, this is let me underline it using my typical set of colors for the underlines. Euler basis is typically the basis using which the angular velocity of the body is written. Okay, this is the basis based on which omega of the coin is expressed, and we see that omega of the coin was phi dot Ez theta dot E1 double prime psi dot E3 double prime, which implies that the Euler basis is not an orthogonal basis because Ez is not perpendicular to E1 double prime and E3 double prime. Okay, Ez is not perpendicular to E1 double prime and E3 double prime, which implies that the Euler basis is not an orthonormal basis. Okay, so this is a point that we had made in the previous class, so I'm not going to harp on it too much. The upshot is it's not a huge deal for us. We can always take these vectors, since we have the transformation matrices. We can express them in terms of one set of common unit vectors or the other. Okay, my choice is typically to express them in terms of the xyz coordinate frame and then also the double prime coordinate frame. Okay, and you'll see the reasons for that as we look at solving the rolling coin problem. Okay, so what I'm going to do next is the following. Okay, the next step is we will now express. Okay, next we shall express omega coin on a consistent basis. That is using either xyz or 1 double prime, 2 double prime, 3 double prime unit vectors. Okay, and that's fairly straightforward. So we have omega of the coin as phi dot Ez, and then this is going to be theta dot E1 double prime, but E1 double prime is the same as E1 prime, as you know, so this I'm going to write as E1 prime, and then I'm going to say that okay, this is going to be psi dot, and this is going to be E3 double prime. Okay, which is the same as E3, and we have made use of the fact that E1 prime is the same as E1 double prime, coincident with that, and then E3 is coincident with E3 double prime. Okay, so we have made use of that. Now if you go back to your transformation matrices, you can see that okay, E1 prime can be expressed in terms of Ex, Ey and Ez, right? So using the coordinate transformation matrices, from page 1 or from lecture 8 notes. Okay, these are matrices. Okay, we can say the following. Okay, maybe I should just copy one of these creatures here. So if I take this guy, okay, I'm going to take this coordinate frame and then I'm going to bring it down here. Okay, so I can make use of this and see that okay, from here I can say that E1 prime can be written in terms of Ex, Ey, and Ez, right? This is going to be cos phi Ex and then sin phi Ey, right? Because I want to write everything in terms of cos phi Ex, Ey, and Ez. So this is going to be cos phi Ex and then sin phi Ey, okay? And then likewise, I can take E3 double prime, first write it in terms of the E1, E2, E3 prime coordinate ring, okay? So likewise, if I go ahead here and then bring this big guy down, okay, if I copy that and I bring it down here, okay? So likewise, from here, I can say the following. I can say that, okay, E3 double prime can be expressed in terms of E1 prime, E2 prime, and E3 prime. So this is going to be minus sine theta E2 prime and then cos theta E3 prime. But we see that E3 prime is the same as EZ, and E2 prime, as you can see from there, is minus sine phi Ex cos phi Ey, okay, which means that I'm going to take these creatures and I'm going to start substituting them, okay? So this is going to be substituted directly here, okay? That's one substitution. The other substitution is I'm going to take this guy E3 prime and then substitute that right there, okay? Which tells me that E3 double prime is going to be minus sine theta times E2 prime, which is minus sine phi Ex and then cos phi Ey, okay, and then cos theta times E3 prime, which is the same as Ez, which implies omega of the coin is going to be phi dot Ez theta dot, as you can see from here, omega of the coin is theta dot E1 prime and psi dot E3 double prime. Let me copy that creature and bring that down here, okay? So I'm going to probably, well, I guess let me just write it out here because I don't have space to move this guy. So this is going to be E1 prime, which is the same as E1 double prime, and then this is going to be psi dot E3 double prime, and then substitute for E1 prime and E3 double prime in terms of Ex, Ey, and Ez, okay? And that's essentially what we have done here. We have E1 prime and then E3 double prime, right? So I'm going to copy that guy, okay, and then bring that down here, okay? So we have this creature here. I'm not going to go through all the steps. And then we have I guess this creature which was written down here, okay? We had these written down here, and all I'm going to say is, okay, I'm going to take this guy using a different color, and I'm going to substitute this entire thing onto that, okay? And then I'm going to take the other one, which is this entire thing, okay? And then I'm going to take that and substitute that on to there, okay? And if I do the substitutions and I write omega coin with respect to the XYZ coordinate frame, okay, then if I write omega coin will now be expressed in terms of the Ex, Ey, Ez frame, okay? And here is the expression. It's fairly non-trivial. Omega coin is going to be the following, okay? It's going to be theta dot cos phi plus psi dot sine theta sine phi in the Ex direction, okay? Then it's going to be theta dot sine phi minus psi dot sine theta cos phi, it's cos phi in the EY, okay, and then plus phi dot plus psi dot, let me write that properly, psi dot times cos theta Ez, or in the vector form, okay, omega coin with respect to the x, y, z coordinate frame is going to be the following. It's going to have three components, okay. This is going to be phi dot cos theta dot cos phi plus psi dot sin theta sin phi. Then it's going to have theta dot sin phi minus psi dot sin theta cos phi, and then the last one is going to be phi dot plus psi dot cos theta, okay. Let me write that out properly, did not come out well. So psi dot cos theta, these are the components along the Ex, Ey and Ez coordinate unit vectors, okay. In the, this is in the Ex, Ey and Ez frame. Alright, so this is an important expression, so I'm going to put a box around it so that we can make use of it again. Today my straight line game seems to be a little better. Okay, I'm just going to duplicate that and bring that creature down here, and then complete this nice little rectangle here, okay. So this is an important thing. Alright, and one other thing that I'm going to do is I'm going to write omega of the coin in the double prime coordinate frame, and you'll see the reason for this as we go further, okay. I'll tell you why we wrote these things the way we wrote these things, okay. So we will also write, we shall also write omega of the coin in the E1 double prime, E2 double prime, E3 double prime frame, and the reasons will be explained as we go below. As we proceed further. Okay, this is not too bad, okay. So we already have omega of the coin as phi dot Ez theta dot E1 double prime, right, as a theta dot, and then we have this as a psi dot E3 double prime. The only thing we need to do is express Ez in terms of E1 double prime, E2 double prime, E3 double prime, okay. So which means we need to express Ez in terms of E1 double prime, E2 double prime, E3 double prime. Okay, this is not too bad, and what I'm going to do is the following. I'm going to do this a little quickly, okay, with your silent permission, of course, okay. So I'm going to go from before, okay. We have the following, okay. We'll skip some steps. So this is the situation we had from before, okay. So I'm just going to copy that and bring that here, okay. This is from before. I guess I need to move this up a little more. Well, my copy game is not that good today, okay. So this automatically implies that if I write Ex, Ey, Ez is going to be the transpose of the rotation matrix that we have okay, and this is going to be cos phi sine phi 0 minus sine phi cos phi 0 0 0 1 times e1 prime e2 prime e3 prime, okay. And if for example if I had called this as R1, then this creature is going to be R1 transpose, which is the same as R1 inverse. This is because R1 is an orthogonal matrix, which implies that R1 transpose is the same as R1 inverse, okay. And so I can immediately see, of course, there is not much to see here. We can see that EZ is the same as E3 prime, okay. EZ is the same as E3 prime, but then we need to write E3 prime in terms of E1 double prime, E2 double prime, and E3 double prime. So from before, I'll once again do this pretty quickly. From before, we have this following equation, right? We have this transformation, I'm sorry. So if I copy that, okay, and I bring that creature down here, okay, so this is the situation that we have. This implies the following, implies that E1 prime, E2 prime, E3 prime is going to be the inverse of that rotation matrix. So that's going to be 1 0 0 0 cos theta, and then it's going to be sine theta 0 minus sine theta cos theta. I'm sorry, that's a matrix multiplied by E1 double prime, E2 double prime, E3 double prime, where I call this as R2, and this creature is going to be R2 transpose, which is the same as R2 inverse. This is an orthogonal matrix, orthogonal coordinate transformation matrix, which implies that R2 transpose is the same as R2 inverse, okay. And I can immediately see that E3 prime, which is my EZ, can be written in the following manner. So this implies that E3 prime is going to be written in terms of E1 prime double prime, E2 double prime, E3 double prime in the following manner. So this is going to be sine theta E2 double prime, and then it's going to be cos theta E3 double prime, okay. So this is fairly straightforward, which means that E3 prime is equal to EZ is just essentially going to be the same thing. And I'm just going to copy this and paste that here, okay. So copy that and I'm going to paste that here. Of course, maybe I should do it in the next line, okay. So let me not do that. So this implies the following. So this implies that E3 prime, which is equal to EZ, is equal to that thing that we just copied down here, okay. All right, and so this tells me the following, okay. If I take these and scoot them up a little more, okay, this tells me the following, which means that omega of the coin, if I write it in the form of a column vector, so this tells me that omega of a coin with respect to the E1 double prime, E2 double prime, E3 double prime coordinate frame is the following, okay. This is going to be theta dot, because that's the only component in the E1 double prime direction. Then I'm going to have phi dot sine theta, and then lastly I'm going to have psi dot plus phi dot cos theta, okay. Psi dot plus phi dot cos theta, and I'm just going to call this for convenience as omega of the coin in the double prime coordinate frame, okay. So what we have so far is the following. So far we have omega of the coin in the double prime coordinate frame, okay, in the double prime coordinate frame is this creature here, and I'm going to put this in a box as well. We're going to be calling this pretty often. Okay, so that is this creature, and let's see, red color. Okay, and let me duplicate that, bring that creature down here, and then complete my nice rectangle. I hope all of you are staying awake while I'm doing all these kinds of things. Okay, and then I have the other one as well from here. Okay, this is omega in the XYZ coordinate frame, so I'm going to copy that and bring that creature down there. Okay, so this is going to be what I'm going to be left with. Okay, so this is omega in the XYZ coordinate frame, and I want to get rid of this guy. Okay, so this is in the double prime coordinate frame. E3 double prime frame, and this is in the EX, EY, EZ frame. All right, what am I going to do with all these things? Okay, here is the basic idea. So now my next step is to start by taking a look at the constraint equation. Okay, so the constraint equation, for this I need one of the figures from above. Okay, or perhaps I can actually capture a figure from one of our previous lectures. So let me do that actually. Okay, so I'm going to do this. I've never tried doing this before, so I'm going to go ahead, take this up. Okay, and not sure if I can do it. Okay, I guess it doesn't let me do it. So I'm what I wanted to do was I wanted to capture the figure of the coin. So I tried to go to the previous lecture and then start taking that figure, but it does not let me do it. So I'm left to my own devices. But no matter. I have the following figure here. Okay, so I'm going to copy this guy. Okay, so I'm going to copy that, and then I'm going to bring that creature down here. Okay, I guess I have to paste the image, right? That makes sense. And let me crop it up so that I get rid of some of these distractions. Okay, and that is the situation that I have. All right, and I'm going to increase the size of this image a little bit. Okay, so here is what we're going to say. Okay, the center of mass of the body is this point here, right? So this is the center of mass, which is labeled as G in the figure. I just want to brighten that out. Okay, so that is the center of mass G, and then here is the contact point, which we called as point C. Now you see that the radius is going to be pointing along the direction of the E2 double prime vector. Okay, so the position vector, so note from this figure, that the position vector from contact point C to the center of mass G is directed along the E2 double prime unit vector direction. Okay, which means that I know the position vector from the point C to the point G can be written as R times E2 double prime. All right, and so I'm going to now make use of the constraint equation. Okay, so look at the constraint equation. Constraint equation. Okay, this is the next key step. Okay, once we do this, then we are almost on our way to calculating the equations of motion of this entire thing. Okay, so if I look at the constraint equation, before that I have to write the following. I have to write the velocity of point G with respect to a fixed point. Okay, so I start off by saying that R of G slash O is equal to r of g slash c plus r of c slash o. And the constraint equation is that it is going to be rolling without slip. Okay, since it rolls without slip, since the coin rolls without slip on a fixed ground, okay, r dot c slash o, which is equal to velocity of c, is equal to 0, and then here o is a fixed observer. Okay, and so if I take the differentiation, let me go next step. So r g slash o is r g slash c. As you can see, that's going to be r times e2 double prime, and then r c slash o, which means that r dot g, and then this is obviously saying that this is r g. We usually drop the subscript for the fixed observer, so r g is r e2 double prime, and then r c. So r dot g, which is equal to velocity of g, this is going to be d by dt of r e2 double prime plus r dot c. Okay, or I can write the following: velocity of g is going to be d by dt of r e2 double prime plus velocity of c, but the velocity of c is 0 because we are making use of the rolling without slip constraint. Okay, this is due to the roll without slip constraint. Now what we have is the following. So this implies that Vg is going to be d by dt of r e2 double prime. Now what is Vg? We know rg slash o, which is rg, can be written in terms of the configuration coordinate. This is the location of the center of mass, right? So this can be written as x ex, y ey, and then z ez. Ex, ey, and ez is a frame that does not rotate. Okay, which means that if I do the differentiation, I get Vg is going to be x dot ex, y dot ey, z dot ez, and then note e dot x is 0, e dot y is 0, e dot z is 0. This frame does not rotate. This is a non-rotating frame. Okay, so I have this expression here. This is the velocity. Let me put a box around it, so I'm going to make use of it again. Okay, so this is the velocity vector for the center of mass, but we have some work to do. Okay, so we're going to say that Vg is going to be d by dt of r e2 double prime, which is going to be r dot e2 double prime, and then r e dot 2 double prime. Obviously the radius of the coin is a constant, so this term is going to be gone, which tells me the following: that Vg, which is going to be x dot ex, y dot ey, z dot ez, this is going to be r times e2 double prime. We got to make a note here. E2 double prime dot is going to be omega of the coin crossed with E2 double prime. Okay, which means that this is going to be omega of the coin crossed with E2 double prime. Now you see that I'm going to bring in the expression for omega of the coin written with respect to the EX, EY, EZ coordinate frame, and this is the reason why we wanted the EX, EY, EZ coordinate frame. Okay, so note, we shall now use omega of the coin written using the Ex, Ey, Ez unit vectors. Right? This was the reason why we had expressed it earlier in that manner. Okay. This was the reason, right? This creature here was the reason, because these quantities on the left hand side are in the Ex, Ey, Ez coordinate frame. We want to write everything else on the right hand side in the Ex, Ey, Ez coordinate frame as well. This was the reason we wrote omega coin in the XYZ frame. All right, and so we have to also write E2 double prime in terms of Ex, Ey, Ez. Okay, so we also have to write E2 double prime in terms of Ex, Ey, and Ez. Okay, this is Ex, just in case. Okay, in terms of Ex, Ey, and Ez, and this is fairly straightforward. We had done this earlier, so let me just scoot up a little bit. Okay, I want to show you a couple of things. We had E2 double prime in terms of E1 prime, E2 prime, and E3 prime, and then I can write E1, E2, E3 in terms of Ex, Ey, Ez. So I'm going to take this guy here, okay, with your permission once again, and I'm going to copy that. Okay, so this is from before. Okay, so which means from before I have this guy, which implies that E2 double prime is, you can write it in terms of E1 prime, E2 prime, and E3 prime as cos theta E2 prime plus sin theta E3 prime, and from before we also had the following, right? We had, I'm just hopefully not making you dizzy by going up so fast. All right, I'm going to take this creature here. Lots of coordinate transformations again and again and again. This is the problem with the rolling coin. The problem with any 3D coordinate frame problem is that you're going to have lots of coordinate transformations from one frame to the other. So you got to keep track of it. Majority of these 3D problems is essentially bookkeeping. So if you're good at accounting, you might probably be good in dynamics as well. That was meant as a joke. So I have E2 prime and E3 prime as the following. So from here I can say that E3 prime is the same as Ez, and then E2 prime, as you can see, is minus sin phi E1 cos phi sin phi Ez, and then cos Ex, and then cos phi Ey. So substituting everything, which eventually tells me that E2 double prime is going to be the following. Okay, so I'm going to take E3 prime, plug it in there, then I'm going to take E2 double prime, E2 prime, and then plug that creature in there, so that I write E2 double prime in the following manner. So if I do all the math, crunching and all that, I get the following. So this is going to be minus sin phi cos theta, sin phi cos theta Ex. Okay, then I'm going to have a cos phi cos theta Ey. Okay, and then plus a sin theta Ez. And then we can say the following. Okay, we can say that go back to, now we can use this, now substitute for omega coin and E2 double prime, both written using unit vectors of the EX, EY, EZ frame into the constraint equation. Okay, and here is the constraint equation. Okay, constraint equation was the following. I had x dot ex plus y dot ey plus z dot ez. This is equal to r times omega coin crossed with E2 double prime, okay, where E2 double prime is going to be the following. I'm going to take this big guy here, okay, copy that and then paste that here. Okay, so that's going to be E2 double prime, and omega coin, which I'm going to write as in the xyz system as omega x, omega y, omega z. Okay, this is going to be from before. I'm going to take that thing that we spent a good amount of time trying to write out. Okay, so that's going to be this guy here. Okay, and then bring that here. And of course I'll get rid of this, and that's equal to that. Okay, this is with respect to the xyz coordinate frame. And then we also make use of the fact that cross product can be written using the skew symmetric matrix. From long time back I had mentioned this idea to you. Okay, we can express the cross product using a skew symmetric form for omega coin. Okay, which essentially means that omega coin crossed with E2 double prime, I can write it in the following form. Okay, we had done this earlier. Okay, we had done this earlier in the semester. Okay, this was done when we were talking about angular momentum of rigid bodies. We were trying to come up with the moment of inertia, tensor, and so on. So here is the skew symmetric matrix. So this is 0 minus omega z, omega y, omega z, 0 minus omega x. This is minus omega y, omega x, 0, multiplied with the E2 double prime, which is going to be the following. So that's going to be minus sine phi cos theta. Okay, then this is going to be cos phi cos theta, and then lastly I have sine theta. All right, so we are slowly making a good amount of dent into this problem. This is you can see that there is a reason why this is called the culmination of one of the learning points in at least advanced undergraduate dynamics. If you can come up with the equations of motion for a rolling coin, that's a significant achievement for any advanced level undergraduate-ish dynamics course. Of course, when you go to an actual advanced course, you will start looking at a qualitative analysis of the rolling coin behavior. You will start looking at the stability analysis of the rolling coin and so on, something that we will not have time to do in this course. But if you take advanced dynamics, that is something I'm pretty sure that any person who teaches that course will be doing it. Okay. excuse me. And so what we are going to do is the following. So I have, after the cross product has been computed, okay, after the cross product has been computed, okay, that is that guy there, I'm going to end up with the following. Okay, so I'm going to have what I'm essentially going to do is I'm going to take the EX terms on all the sides and then compare them with respect to each other, EY terms and EZ terms. So before I do that, let me write out the following. So I'm going to have X dot EX, Y dot EY, Z dot EZ. This is going to be the following. It's going to be a big nice mess. Okay, so this is going to be minus R cos theta cos phi, minus R phi dot cos theta cos phi, plus R theta dot sin theta sin phi, okay, minus R cos phi phi dot, minus R psi dot cos phi. This is in the EX direction, okay, plus similar set of terms in the other two unit vectors as well. Okay, I have the following, and I'll write it in a nicer way, as you'll see very soon. So minus R sin phi cos theta, okay, and this has to be multiplied by a certain term which I usually keep forgetting, phi dot sin phi cos theta, plus minus R sin theta cos phi theta dot, minus R theta dot sin theta cos phi, plus minus R psi dot sin phi. This is in the EY, and then plus I'm going to have something in the EZ coordinate unit vector direction. This is going to be R theta dot cos theta. Such a nice simple thing, R theta dot cos theta EZ. Okay, comparing the terms on either sides. Okay, comparing the EX, EY, EZ terms on either sides, on both sides of the equation. Okay, the constraint equation can be written in the following form. Okay, the constraint equation for a coin rolling without slip on fixed ground, fixed rough horizontal ground, is the following. Okay, that's going to be three things. X dot is equal to minus R cos theta cos phi phi dot. Okay, then I'm going to have R sin theta sin phi theta dot, plus minus R cos phi psi dot. Then Y dot is equal to minus R sin phi cos theta phi dot, minus R cos theta sin phi phi dot. Then I'm going to have minus R sin theta cos phi theta dot, plus minus R sin phi times psi dot, and then Z dot is going to be R times cos theta times theta dot. Okay, so this is one of the premier things that we have, the constraint equation. Okay, so I'm just going to write it out. This is fairly important stuff. I'm going to duplicate that and bring that down here. Okay, so that I can write it out completely. And this is a significant achievement for us in this particular problem. And I'm going to take these guys down here and then scoot them down a little bit more so that we have space to write certain things, or space to maybe put a nice box around them. I'm going to put a box in the color blue. Okay, so I need to make sure that line is drawn that way. Okay, this is duplicate that and then bring that creature down here. Almost there with the end of this problem. I promise you it will not be that painful from now on. Okay, and here is what we will get. Okay, so these are the constraint equations. So there are three constraint equations. Okay, this is equation A, equation B, equation C. Okay, so we have three constraint equations. Okay, and what I'm going to say is, by inspection, I'm not going to prove this. It is fairly straightforward to look at it. We can write this in the Pfaffian form, which I'm going to do anyways. Okay, I'm going to write this in the Pfaffian form for the constraint equation, and then we can easily prove that these equations are, the last one, the equation C, is a holonomic constraint, and then the other two are non-holonomic constraint. Okay, so this is the only holonomic constraint here, so this is going to be holonomic constraint, but unfortunately that is not the case with the above. So we can we have three constraint equations, and from inspection we can see that if I look at z dot, this is r cos theta times theta dot, which implies that dz is r cos theta times d theta, which means that this is integrate, I get z is r sine theta, which means that this is an integrable constraint. Okay, so which implies that the z dot is equal to r cos theta times theta dot. This is an integrable constraint. Okay, so that is one key thing that we have found out. But then the other two constraints, constraints A and B, are non-integrable constraints or non-holonomic constraints. So this is a holonomic constraint. Okay, okay, but by inspection, I'm not going to prove that, but by inspection, constraints A and B are not integrable. Okay, which means that they are non-holonomic constraints. Okay, so which means that non-holonomic constraints for this problem are the following. For the rolling coin are the following. Okay, these two fellows here. So I'm just going to copy these two guys and then bring them down here. Okay, I'm sorry, I shouldn't have cut them. I hope I can still do the pasting here. Okay, that's really nice. Okay, then I want to take this guy and let me roll this down a little bit. I hope it lets me do that. Probably might. I'm going to take this and bring that down here. So these are non-holonomic constraints here for me, both of these. Okay, this is by inspection, but one can also prove. Okay, can also prove by writing the Pfaffian form. And testing for integrability. Okay, so these are non-holonomic constraints. The holonomic constraint for the rolling coin is the following. For the rolling coin is z dot is equal to r cos theta times theta dot, which means that z is r times sine theta. Okay, so this is a as a holonomic constraint, so I'm just going to copy that and underline that here. Okay, and so we see that since all the constraints, not all the constraints are holonomic, this is a non-holonomic system. Okay, so this is a key point. Okay, so key point, since not all constraints are holonomic, the rolling coin problem in 3D for roll without slip is a non-holonomic system. Okay, that's the key point that we are making use of. In 3D for rolling without slip is a non-holonomic system, which means that if you have to solve this problem, you have to use the idea of Lagrange multipliers. Okay, so which implies, okay, so note that to obtain solution of the problem, that is the equations of motion, we have to use Lagrange multipliers. For the problem of the rolling coin. Okay, to obtain the equations of motion, and also of course to solve for the constraint forces. The constraint forces, if I don't use a holonomic constraint, these are essentially going to be the friction forces in a two direction. Okay, so I'm just going to make a brief note, one more note. Okay, the constraint is the static friction force at the contact between the coin and the ground for the non-holonomic constraints. And the constraint for the let me rewrite this, it doesn't look too great to me. The constraint, the static friction force, is the contact for the non-holonomic constraints. Okay, and for the holonomic constraint, okay, is the normal force between coin and the ground for the holonomic constraint. So which means that I'm going to have one of these, and then I'm going to have two of these. Okay, because I'm going to have two friction forces at the contact surface. Okay, so what's my next step? My next step is to take these and I'm not going to make use of the holonomic constraint because I already know it is integrable. So I'm going to take some shortcuts and I'm going to say the following. Okay, so to take some shortcuts. I will directly substitute for the holonomic constraint wherever I see as z dot. Okay, so I will directly use the holonomic constraint, the integrated form of the holonomic constraint in the Lagrangian. Okay, as you will see. Okay, directly use the integrated form of the holonomic constraint in the Lagrangian. Okay, which means that to solve the problem I need the following. So first of all, let's take a look at it. Okay, we have from earlier the number of configuration coordinates are 6. Okay, so 6 configuration coordinates, 3 constraint equations, two of them are non-holonomic, and one is a holonomic. Okay, which essentially tells me that first of all, system is non-holonomic. Okay, then it also tells me that the number of degrees of freedom is going to be the number of configuration coordinates minus the number of constraints. Which is going to be 6 minus 3, which is going to be equal to 3. Okay, and this also tells me that okay, if this is indeed the case, then how many equations of motion can we expect? Okay, so we can expect 3 equations of motion for the rolling coin. But since the system is non-holonomic, we cannot find any generalized coordinates to write the equation of motion, which means that so we have to use Lagrange multipliers to solve the problem. Okay, and so let us go on that particular route, but before that I have to write the kinetic energy and the potential energy. So let me do that. Okay, so we shall write the kinetic energy and the potential energy in terms of the configuration coordinates. Okay, so that is the next step, and then we will make use of the two non-holonomic constraints. We will substitute. We shall substitute for z is equal to r sine theta, which means that this constraint equation has been used, so we need only two Lagrange multipliers. So we need only two Lagrange multipliers to account for the other two constraint equations. For the other two constraint equations. Okay, that is if we did not use z is equal to r sine theta, if we did not use z is equal to r sine theta, which was obtained, I guess I should write that a little better, which was obtained by integrating the third constraint equation then we would have needed three Lagrange multipliers to account for all the three constraints. Okay, but since we are substituting for z is equal to r sine theta, but since we will substitute z is equal to r sine theta, we need only two Lagrange multipliers. All right, so this is almost there, maybe 10 more minutes and then I'll be done with this problem. So the first thing I'm going to write is the kinetic energy. Okay, so kinetic energy is going to be T. First of all, we got to make sure that this is a rigid body, so rolling coin is a rigid body. Rolling coin, rigid body, which means that T is going to be T translation plus T rotation. Right, translational kinetic energy plus rotational kinetic energy, which means that I'm going to have T is going to be half mvg square and then half times omega coin transpose I center of mass omega coin. Okay, this is the translational kinetic energy, as you know from before, that is that guy, and then I have the rotational kinetic energy, that is that creature there. So let me write out the following. Okay, so from before we have Vg is x dot ex, y dot ey, z dot ez, which implies that Vg square is going to be x dot square, y dot square, z dot square. Okay, and then I'm going to substitute z dot is equal to r cos theta theta dot from the third constraint equation Okay, and so Vg for me, which becomes the following. Vg square is x dot square, y dot square, and then r cos theta times theta dot whole square. Okay, so that's going to be Vg square, and then likewise I'm going to have omega of the coin. I'm going to write it using the E1 double prime, E2 double prime, E3 double prime coordinate frame. I mean, this is just because, you know, I can write it using any frame I want, right? I mean, there is not it's not much of a big deal, right? So I'm going to just make use of that and say omega of the coin using the E1 double prime, E2 double prime, E3 double prime coordinate frame. This is the following. This is something that we had derived a little while back. So this is going to be theta dot, then this is going to be phi dot sine theta, and then psi dot plus phi dot times cos theta. Okay, this is another thing that we have. And then lastly, moment of inertia. Of course, fairly straightforward. Let me draw a quick picture. I mean, here is the rolling coin. Okay, so if this is the situation that I have for the rolling coin, then I set up the axes, the coordinate frame. This was the contact point C. This was the center of mass G, right? And here was one of the axes that we had. This was the E2 double prime. Let me maybe write G a little off here. So this is going to be the center of mass G. Okay, this was the contact point C on the ground, and here was one of my directions. So this was E2 double prime. Then this creature here is going to be E1 double prime, and then coming out of the page, which I'm going to draw in the red color here. Okay, that's going to be, I guess I'm going to show it out a little more. So that's going to be E3 double prime. Okay, this is the coordinate frame that I have, and this is on the same plane as the coin. And so you see that this is a principal coordinate frame. So I center of mass can be defined as the following. Okay, so this is a symmetric, axisymmetric body, which means that you know, I center of mass with respect to the E1 double prime, E2 double prime, E3 double prime coordinate frame is going to be the following. Okay, so let me write that straight. We're almost there. Hang in. This is going to be I1 in the double prime direction, 0, 0, 0, I2 in the double prime direction, 0, 0, and then I3, sometimes I can't write 3, double prime. Okay, but because it's axisymmetric, because the coin is an axisymmetric body, I'm going to say the following. Okay, I'm going to say that I1 double prime is equal to I2 double prime is equal to mr square by 4, I3 double prime, which is equal to I2 double prime plus I1 double prime, is mr squared by 2. This is very basic stuff. Okay, and so this tells me that so say I1 double prime is equal to I2 double prime, and I'm going to call that as I. Okay, so I is mr squared by 4, and then I3 double prime is going to be, I'm just going to call it as I3. Okay, and this is going to be mr squared by 2. Okay, so these are the things that I have, and so excuse me, I can write the kinetic energy, and once we do that, you know, we are almost on our way to this long journey that we have here. Okay, then one more thing that I can show is here I have, if I go back to one of my figures from earlier, let me write the kinetic energy first. Okay, let me finish that off. Okay, so kinetic energy T is now going to be the following. Okay, so this is going to be, if I expand it out, so this is going to be T is equal to half times x dot square, y dot square, r square, theta dot square, cos square theta, right? That was Vg square plus half times, I'm going to say this is omega 1 double prime, omega 2 double prime, omega 3 double prime transpose multiplied by the matrix which I'm going to call as I 0 0 0 I 0 0 0 I 3. Okay, and then I'm going to have omega 1 double prime, omega 2 double prime, omega 3 double prime. Okay, and if I perform these substitutions, I end up getting the following. Okay, we will do that very soon. Let me just write down the potential energy as well, and then we are on our way. To write the potential energy, here is what we need to do. Okay, for the potential energy, I just need to find out what the height of the coin is, center of mass is from the vertical ground. So this is equal to z, right? So the height of the coin, center of mass of the coin, let me write that properly. Height of the center of mass of the coin from horizontal ground, horizontal plane, which is the datum, is z. Okay, which means that potential energy is going to be mgz, which is going to be mg times r times sine theta, where we have substituted for z is equal to r sine theta. Okay, and this is going to be the potential energy, and I'm going to substitute for omega 1 double prime and so on and so forth. And I just want to make a quick note here. This is the same as omega 1 double prime, omega 2 double prime, omega 3 double prime. This is omega of the coin. So I'm going to substitute for all of these quantities. Okay, and here is what the Lagrangian will end up being. Okay, so after substituting, okay, substituting for omega 1 double prime, omega 2 double prime, omega 3 double prime, I, and then I3. Okay, the Lagrangian L is equal to T minus V, which will give me a pretty big character. So this is going to be half m x dot square, half m y dot square. Then I'm going to have half m r square theta dot square cos square theta. Okay, then after the substitutions have been performed, I have a whole train of terms here. This is going to be mr square by 8 theta dot square again. Okay, that's one thing that I'm going to be having. Okay, then I'm going to be having mr square phi dot square sine square theta divided by a factor of 8. Then I'm going to be having mr square by 2 times psi dot plus phi dot cos theta minus mgr sine theta. Okay, so this is the Lagrangian, and I'm going to box this up because this is a singular achievement for us today. Okay, at least for me it is. It takes a lot of time to write these things out. Pretty satisfying to see it all come together. Okay, so this is the Lagrangian. Then what we do is we look at the constraint equations that we haven't used. Okay, so look at the first two. Constraint equations. Okay, I'm just going to take those creatures and bring them down from earlier. Okay, so here is somewhere where I have the constraint equations. So I'm going to take these guys, copy them, okay, and I'm going to bring them here. Alright, so almost there. So I'm going to write the constraint in the Pfaffian form. Okay, so to collect everything, write the constraint in the Pfaffian form. Okay, with your permission I'll complete this problem so that we will be done with the equation of the rolling coin. So if I write the constraints in the Pfaffian form, here is what I have. Okay, instead of x dot and y dot, I'll be having dx, dy, and so on. Okay, so here is the first one. Okay, so the first one is going to be 1 times dx plus, a big bracket starts, then 0 times dy. Okay, so plus 0 times dy plus 0 times dz. Then I'm going to have terms containing d phi, d theta, and d psi. Okay, that's going to be plus r cos theta cos phi d phi. Okay, then I'm going to have plus minus r sin theta. Let me write that in the next line. Okay, plus minus r sin theta sin phi d theta plus r cos phi d psi, that is equal to 0. This is the first constraint equation written in the Pfaffian form. The second constraint equation likewise is going to be 0 times dx, 1 times dy, 0 times dz. Then I'm going to be having r sin phi cos theta. Okay, so r cos theta sin phi d phi plus r sin theta cos phi d theta plus r sin phi d psi. This is equal to 0. Okay, so this is the constraint written in the Pfaffian form. And then we have the Lagrangian. Okay, the Lagrangian is from here. So these are the things that we really need, and I'm going to put this in the box as well. So this is also a pretty key thing. I guess that doesn't look like a straight line in anybody's book. Okay, I'm going to expand that and then bring that down here so that we're almost on our way to write the equations. I really appreciate your patience in sitting through these lectures. I know that in person probably would have been maybe more painful. Alright, so this is the constraints written in the Pfaffian form. There are 2 constraints, so I need 2 Lagrange multipliers. Okay, 2 non-holonomic constraints. Okay, so here are my Lagrange equations, okay, written for the entire problem. Okay, so the Lagrangian formulation. Okay, lambda 1 and lambda 2, these are multipliers for the first and the second constraint equations, okay, which are shown above here. Okay, and here is the formulation. So here are my equations. I'm going to have 6 of them. Okay, so first one is going to be for the x term. So this is going to be d by dt of dl by dx dot. This is going to be dl by dx plus qx non-conservative plus summation j is equal to 1 to 2 lambda j aji, okay, or ajx, I guess, in this situation. Okay, then my second one is going to be d by dt dl by dy dot is equal to dl by dy plus qy non-conservative summation j is equal to 1 to 2 lambda j ajy. Okay, then third one, d by dt, and I don't have a z dot in this situation, so I just going to have a theta dot. Okay, so I have swallowed that up, so that's going to be dl by d theta dot. It's going to be dl by d theta q theta non-conservative lambda j is equal to 1 to 2 lambda j aj theta. Okay, then the fourth one, d by dt dl by d theta dot is phi dot, that's going to be dl by d phi plus q phi non-conservative summation j is equal to 1 to 2 lambda j aj phi. And the last one, d by dt dl by d psi dot is dl by d psi q psi non-conservative, okay, plus summation j is equal to 1 to 2 lambda j aj psi. Okay, so these are all the equations from here, and we can write aj x a1x and a2x and so on and so forth from here. So maybe I can just sneak in and then write those things here. Okay, so this is going to be a1x, this is going to be a1y, this is going to be a1z. I guess in a sense I don't have the dz term. Okay, this is going to be a1 phi. Okay, let me write the phi properly. So this is a1 phi, this term is going to be a1 theta, and then this term is going to be a1 psi. Okay, and likewise this is going to be a2x, this is going to be a2y. Okay, I don't have the z, I'm not too worried about that. That's going to be a2 phi, that's going to be a2 theta and a2 psi. Okay, so these are the terms. I know that we are almost at the end of the journey here. So my situation is I'm not going to go ahead and do them completely. Okay, I'm going to take some liberties here. So these are all the AJs that I have here. Okay, so what I can say is the following. Okay, first of all, there are no non-conservative forces in our situation. Okay, so that's gone, that's gone, that's gone, that's gone, that's also gone. Okay, so this is a conservative non-holonomic system. Okay, so this is a conservative non-holonomic system. Okay, it is conservative because there is no kinetic friction. Okay, it is conservative because due to static friction from roll without slip constraint. Okay, if you had the kinetic friction, then this would be a dissipative system. Okay, the approach is going to be pretty similar to this, but there will be some qualitative differences between the two. Okay, that will be there will still be one constraint which will be the normal force, but then we will be having the other two which will be in the form of non-conservative forces, so there will be no need for the Lagrange multipliers from that perspective. Okay, all right, and so I'm going to go ahead by looking at each of these. So I'm going to start off. Okay, so simplifying. Okay, here is what I end up having. Now lambda j a j x. So let me rewrite these things a little more better. So I'm going to copy these same things. Going to get rid of some of the terms. Okay, so I don't think I have, maybe I don't have enough space here, so let me write the first set of terms. Well, probably not. So let me say that I'm going to start simplifying things. Okay, so we shall now substitute for Lagrangian and the Pfaffian coefficients. Okay, that's something that we're going to be doing. Okay, so in this situation, if I start pasting this here, so the equations from before, so I'm going to get rid of some of these terms here. Okay, that's gone for me, that is gone for me, that is also gone for me, that creature is also gone, vanished, that creature is also gone. Now if I take this guy and if I cut that out, so this is going to be lambda 1 a1x, lambda 2 a2x. Okay, then likewise I'm going to take all of these guys and get rid of them. Okay, and then I can write this is going to be lambda 1 a1y, lambda 2 a2y, then lambda 1 a1 theta, lambda 2 a2 theta, lambda 1 a1 phi, lambda 2 a2 phi, and then lastly I have lambda 1 a1 psi, lambda 2 a2 psi. Some of these things cancel off. I don't have this one and I don't have that term, but the rest of them still remain for me. Okay, so once I do the substitutions, here is what I end up getting. Okay, so after the substitutions, here is what I end up getting. So this tells me from the first one I'm going to be getting d by dt of mx dot is going to be lambda 1. Okay, so that's going to be lambda 1 times 1. Then from the second one I'm going to be getting d by dt of my dot is going to be lambda 2 times 1. So this essentially tells me that lambda 1 is mx double dot. This tells me that lambda 2 is my double dot. I'm going to put a box around these guys because I will need them again. We're almost there. Okay, hang in, end of the journey. There's one more lecture also left, so that's also something that's nice. Then I have the rest of them. Okay, from the third one, that's going to be the d by d theta thing. So here is what I'm going to be having. So that's going to be d by dt of mr squared by 4 theta dot. So if I go back to the Lagrangian, okay, so if I look at the Lagrangian, there is this term containing theta dot. There is also another term containing theta dot right here, okay, which is going to be half mr squared theta dot square cos square theta. So if I do the differentiation, that's going to be mr squared theta dot cos square theta. Okay, so that's going to be plus mr square theta dot cos square theta. This is going to be equal to the following. Okay, I'm going to have many terms containing theta, so I'm going to start putting a bracket here. Mr square by 4 phi dot square sine theta cos theta. I'm writing the steps after the simplification has been done. Okay, mr square by 4 phi dot square sine theta cos theta. Then I'm going to be having minus I had an mgr sine theta, right? So that's going to be minus mgr cos theta. Then I'm going to be having minus mr square times psi dot plus phi dot cos theta multiplied by minus phi dot sine theta. Okay, that's one thing. Then I'm going to be having plus lambda 1 times minus r sine theta sine phi, and then I'm going to be having plus lambda 2 times r sine theta cos phi. Okay, that's one big thing. And then the fourth one, that's going to be d by dt with respect to phi dot, so that's going to be mr square by 4 phi dot sine square theta from the Lagrangian. I'm skipping the details of that. Okay, this is and of course I'm going to have an extra term here. Okay, so plus d by dt. There are two terms in the Lagrangian containing phi dot. I just want to point that out. Okay, there is one term containing phi dot here, there is another term containing phi dot there. Okay, so that's something that I wanted to point out. And so if I go ahead and do that, that's going to be plus d by dt of mr square times psi dot plus phi dot cos theta. Okay, this is equal to the following. It's going to be lambda 1 times r cos theta cos phi plus lambda 2 times r cos theta sine phi. Okay, this is the penultimate one, and this is the last one now with respect to psi dot. So that's going to be d by dt of mr square times psi dot plus phi dot cos theta. Okay, this is equal to lambda 1 big bracket lambda 1 times r cos phi plus lambda 2 times r sine phi. Okay, so these are our equations so far, and here is a strategy. Okay, now what we're going to do is this. Okay, so how to go further is this. Okay, so now look at equations 1 and 2. Okay, look at that. So this is equations 1 and 2. So from here, this is what I end up getting. Okay, I copy that and I paste that here. Okay, this is equations 1 and 2. Then we already have lambda 1 as mx double dot and lambda 2 as my double dot, but we have a relationship between x dot and theta dot phi dot psi dot and y dot and theta dot psi dot phi dot from our constraint equation. Right, I'm going to pull that in, okay, with your permission. So here is that equation. I'm going to copy that and then paste that here. Okay, that's coming from here, which means that if I differentiate the above, we can get lambda 1 and lambda 2 in terms of the Euler angles. And that's exactly what I'm going to be doing. Okay, so this essentially tells me the following now. Okay, this tells me that lambda 1 is mx double dot, which means that lambda 1 is going to be d by dt of that entire expression here. So this is going to be d by dt of this expression here. Okay, so I'm going to bring that creature in, copy that and paste that here. Okay, I guess that's not going to be enough space for me, so I'm going to I guess get rid of some of these. Okay, so this is going to be m times d by dt of this expression here. Almost there. Okay, that's the creature there. Okay, that is d by dt of that. And then, so after doing the differentiation, I get the following. Okay, bear with me please. This is going to be m times minus r cos theta cos phi phi double dot phi double dot, okay, plus r phi dot theta dot sin theta cos phi, okay, plus r phi dot square cos theta sin phi, plus r theta double dot sin theta sin phi, plus r theta dot square cos theta sin phi. Keeps going, the gravy train. Theta dot phi dot sin theta cos phi, two more terms, minus r psi double dot cos phi, plus r psi dot phi dot sin phi. Okay, so that is one thing, and I'm going to put a bracket around this. Okay, so that is one, and likewise we will be having something similar for the other term as well. Okay, so let me pull this down. So that's lambda 1. We found out one of the multipliers, and likewise lambda 2 is my double dot, okay, which implies that lambda 2 is going to be m times d by dot of the following quantity, which I have to get from here. Copy that and then paste that down here. Okay, have that almost done. I guess I can clear up some of these and bring that here. Okay, and maybe take this entire thing and slide it down a little so that I have some space to make this slightly better. And so this tells me that I know lambda 2 is going to be m times differentiation of that big creature. Likewise for the previous case, so r sin phi cos theta phi double dot, then I'm going to have an r phi dot theta dot sin phi sin theta, then minus r phi dot square cos phi cos theta. There is not much of a brain involved in this. This is just a brute force differentiation, so there is not much to do here. So r theta double dot sin theta cos phi minus r theta dot square cos theta cos phi plus r phi dot theta dot sin theta sin phi. Almost there, almost there. Minus r psi double dot sin phi minus r psi dot phi dot cos phi. Okay, and then I'm going to duplicate these guys and bring them here so that we have these written in a nicer way as well. Okay, and the very last step, I guess. Okay, this is these are the two things that I have. So these are the two multipliers, and then my final step is the following. Okay, so final step, view, okay, is to substitute for lambda 1 and lambda 2 into equations 3, 4, and 5. Where 3, 4, and 5 are the following. Okay, I'm hoping I can get these guys all together in one single shot. I think I should be able to. Okay, so copy that, and then I'm going to bring that down here. Okay, so these are equations 3, 4, and 5, where we're going to be substituting for these guys. Okay, these lambda 1 and lambda 2, lambda 1 and lambda 2, lambda 1 and lambda 2, and I'm going to make use of some simplifications. Okay, so we're also going to make use of also say that I is equal to mr square by 4, I3 is equal to mr square by 2 in the theta, phi, and psi equations. And so we have the final set of equations. For the rolling coin are the following. Okay, so the final set of equations. Okay, I have already done the differentiation, and I'm going to just write them out. Okay, so these are the final set of equations. So that's the first one is the following. So that's going to be I. Let me make sure that I have all the equations written out properly. Okay, the first set of equations are the following. So they're going to be I phi double dot sine theta. Okay, plus 2i times phi dot theta dot cos theta. Okay, minus I3 theta dot times psi dot plus phi dot cos theta is equal to 0. This is an equation of motion. Okay, then the second equation of motion is the following. Okay, that's going to be I plus mr square. Okay, this is going to be theta double dot plus I3 plus mr square okay times phi dot sine theta times phi dot cos theta plus psi dot. After all the hard work has been done, okay, then I'm going to have a minus I times phi dot square sine theta cos theta. This is one whole equation, okay, plus mgr cos theta. That's equal to 0. Then the third one is going to be the following: I3 plus mr square, and this is going to be the equation for psi double dot. Okay, so this is going to be psi double dot, okay, plus phi double dot cos theta, okay, minus phi dot theta dot sine theta, okay, minus mr square phi dot theta dot sine theta is equal to 0. And then importantly, I'm going to have lambda 1 and lambda 2 from above. Okay, those are my multipliers. I'm just going to copy them out. Okay, so here is lambda 1 so copy that, and bring that creature down here. Okay, so that's one. Then I'm going to have the fifth one is going to be lambda 2. That's the second multiplier. Okay, this is a mind-boggling array of equations, right? Copy that and then bring that down here. We're almost done. I'm going to get rid of some of these terms here. Cut that off and this off as well. And then two more. The constraint equations, the x and the y constraint equations. Okay, so those were written down here. If I recall them, they were from here. Okay, so I copy that, then I bring them here. Okay, so that's going to be 6, this is going to be 7, and then 8 is going to be z dot, which is equal to r theta dot cos theta, or z is equal to r sine theta. And the basic idea is this. Okay, after writing all of these things down, you first have to solve equations 1, 2 and 3. These are your equations of motion. Okay, these are your equations of motion. Okay, which means that if I solve these three, then I can calculate lambda 1 and lambda 2, then I can calculate x dot, y dot and z dot. Okay, so to solve for the equations of the coin, okay, solve equations for theta double dot, phi double dot, psi double dot first. Okay, equations 1, 2 and 3 above, and then obtain lambda 1 and lambda 2, use equations 4 and 5 above. Okay, and then obtain x, y and z by solving equations 6, 7 and 8 above. All right, so this is in my opinion one of the great achievements in dynamics, is coming up with the equations of motion of the rolling coin. I really appreciate your patience. I've gone a little too far beyond our regular lecture time, but I'm assuming that you can watch this at twice the speed, or you can probably come back to this lecture at different points in time in your career and take a look at it if necessary. Okay, I really appreciate your patience. Thank you very much for listening to these lectures, or at least giving it a try. Take care of yourselves. Last lecture is next this Thursday. We will be looking at the equations of a spinning top. I'll be a little quick there. Okay, thank you very much again, and take care of yourselves. Stay safe. Bye.